In this video, we're going to continue studying how taking limits interacts with the composition of functions. In the previous video, we saw that if the outer function is continuous, things are pretty nice. But is that the general case, or do we have some problems when the outer function is not continuous? Well, let's take a look at it and see what happens. My first question is the following. If I know that as x approaches c, g of x approaches L, if I know that the limit as y approaches L of f of y is equal to m, can I say that the limit as x approaches c of f of g of x is equal to m? Let's take an example. Let's see what happens. If I defined f of y to be equal to 2 when y is equal to 1, and 3 when y is different from 1, and g of x is the constant function 1, then the first thing that we notice is that the limit as x approaches 0 of g of x is equal to 1, because g is a constant function. It's also very easy to see that as y approaches 1, f of y approaches 3. So what can we say about the limit as x approaches 0 of f of g of x? Well, to answer this question, we should first know what my function f of g of x is. You see, no matter what number x I pick, I know that g of x is going to be equal to 1. So that means that f of g of x is just f of 1, and f of 1 is equal to 2. So the function f of g of x is just a constant function equals to 2. So the limit as x approaches 0 of f of g of x is equal to 2, which is different from the limit as y approaches 1 of f of y, which was 3. So here we see that we have a bit of a problem. The answer to my question is no. That is not true. And now let's try to understand where the problem is coming from. So the core of the problem is this. You see, the limit as x approaches c of g of x equals L means that if x is close to c but not c, then g of x is close to L. And the limit as y approaches L of f of y equals m means that if y is close to L but y is not L, then f of y is close to m. And here is where things become important, to be very, very picky about the details. I wrote in yellow that y is not L. And this is because of the following. From the fact that the limit as x approaches c of g of x equals L, we know that if x is close to c but not c, then g of x is close to L. But g of x could be L, for example, if g is a constant function, like in the example that we just saw. And then the problem is that if I make y equals g of x, then I cannot properly plug it into statement 2, because I would not have that important condition of y is not L, because, well, y, which is now g of x, could be L. And that is a problem. It doesn't allow me to follow the change of thought. So we cannot concatenate these implications. And I can see two ways of solving this. One way is that I remove that yellow condition of y has to be different from L. And if you see, y close to L means f of y close to m. Well, that would actually bring us to more of the territory of f being continuous, right? Because if y is equal to L, for these things to work, this limit to work, then m would have to be just f of L. So that is one way, which we saw already, but there's another way to solve this problem. It is force my function g to not be equal to L in a neighborhood of c. So making sure that my function g of x is not going to be equal to L when we are close to c. So those are the two options. We just need to deal with this yellow condition and try to find our way around it. So we have two solutions. Solution number one. If I know that limit as x approaches c of g of x equal to L, and f is continuous at L, then the limit as x approaches c of f of g of x is equal to f of L. That corresponds to removing the condition that y has to be different from L. The other solution is that, well, if I say that the limit as x approaches c of g of x is equal to L, and that f of x is different from L for x around c except possibly at c, and I know that the limit as y approaches L of f of y is equal to m, then the limit of the composition g, f of g of x is equal to m. So here you see what we did is, instead of removing the yellow condition that y is different from L, we are forcing that to happen by requiring that g is not equal to L. So again, that shows exactly two possible solutions to go around the problem that we saw. And I will leave for you as an exercise to prove theorem 2, so that solution 2 that we found, prove that this is indeed the case.